Hi everyone, today I'm going to talk about how I did a comprehensive range of advanced deep learning concepts using both TensorFlow and Keras. So first part, it focuses on enhancing model generalization through various data augmentation techniques, often with alpha beta testing wherever required, and also regularization models implemented in TensorFlow. And then in this we have different parts using like L1, L2 regularization, dropout, early stopping, Monte Carlo dropout, diverse suite, initialization strategies, batch normalization, custom dropout and regularization, and also various other things. The use of callbacks and TensorBoard for training management, hyperparameter tuning using Keras Tuner, leveraging KerasCV for image augmentation, exploring data augmentation for diverse data modalities like image, video, text, time series, tabular, speech, document images, and so showcasing the data augmentation capabilities of the fast AI library. So these are the first part techniques that all of this which we're gonna do. So till here, um, yeah, till here demonstrate fast AI data augmentation capabilities. So this is all about the part one. So let's start. So in part one we have all of these which we're going to look at, and then in part two we have I'll be creating a different video for that. So let's go with the part one. So this is for the L1 and L2 regularization. So let me just open that. Just going to open the next one as well, just to make it faster. So in the part one, we explored various methods to improve the generalization of deeper learning models by augmenting training data and reapplying regularization techniques. So here in the first one, we're doing L1 and L2 regularization. So here we're just demonstrating how to apply L1 and L2 regularization to the kernel weights of the dense layers in Keras. And this is the execution what we're doing in collab. So train these models and compare their performance on a validation set to baseline model without regularization. So we're just comparing both of the models, and then how we're gonna observe how L1 leads to drive weights to zero, while L2 penalization when it does the penalization of large weights. So let's go to that. So this is the L1 and L2 regularization. So L1 is also called as lasso and L2 is also called as ridge. So what L1 does is it adds a penalty to the loss function proportional to the absolute value of weights, and L2 it adds a penalty to the loss function proportional to the square of weights. And then here we're doing nothing but we're just comparing L1 and L2. So we're taking the digits data set over here. So taking the data set, importing everything, taking the data set, scaling the data set, splitting it, and then creating the regularized model. So as you can see, L1 and L2 are defined here. So you can see these are the regularizers doing L1 and L2. So this is the model without the regularization. Then we're compiling using the Atom optimizer. So as you can see, this is the model without anything, which is nothing but the base model we're going to be comparing to. And then we just created another model with only the L1, only the L2 regularization. As you can see, L2 is 0.01, and this is the with compiling it and storing it after fitting it. Then we're doing another model where we're doing with only the L1 regularization, and then we're creating another model where we're doing both L1 and L2 regularization. So as you can see, without any regularization, we got an accuracy of 0.97, and then after L2 we got 0.97, the same thing, and then using L1 we got 0.95, and then doing the both combining both L1 and L2 we got 0.96. So this model serves as a control, so that is the model which doesn't have anything. And then with the L2 it applied L2 regularization to the weights of the dense layers, then L1, and then both L1 and L2. So L2 did not show a noticeable improvement, but then L1 regularization it resulted in a slower test accuracy. So it because it encourages sparsity in the weights, which might have led to like some loss of information. So that is why we got kind of less. And then combination of L1 and L2 also kind of showed less than the baseline, although it did perform better than the L1. So this is about using L1 and L2 regularization. let's go to the next part where we're doing the dropout. So we're just illustrating the dropout layers over here to prevent overfitting. So let's just do, so basically all of these are like comparing with the baseline models, nothing but the alpha beta testing. So when here we're going to do the same thing without dropout and then with dropout. So loading the same data set, importing everything, scaling the data set, and then splitting into the training testing. And then this is the model without the dropout. And then we have another model with the dropout. So you can see that the layer is defined over here. Here we just have two different layers, but then here we added the dropout layer to that with a 50% dropout rate. And then we're compiling both the models. This is for the without dropout, this is for with dropout. And then as you can see, we're just printing out the accuracy. So without the dropout, you can see it gave 0.75, and then with dropout, which 50% dropout, we got 0.97. So as you can see, there's an slight difference of 0.02, but if the data set is extensive or if makes where it makes more sense to have a dropout, then we'll be able to see a much larger difference. So we compare the performance of a simple neural network model trained with and without dropout. And then as you can see, the model with dropout regularization achieved a slightly higher test accuracy compared to the model without dropout. So we can say that we can conclude saying that dropout is indeed intended to prevent overfitting by reducing the co-adaptation of neurons. So while the improvement is small, it is still indicating that the dropout is helping with the general model. It is helping the model generalize slightly better to the unseen test data. So this is all about dropout regularization. And then after that, we have the early stopping, where in this we show how to use the early stopping callback to halt training when validation loss stops improving. So basically, we have to prior define how many steps we want to do. But in this early stopping, what we can do is we can define that if there's no improvement in the next step, or if you don't see any improvement across steps, then we just stop it there and then take whatever is the best. So it is a regularization technique that monitors the model performance on the validation set and stops training when the performance improves for a specific number of epochs, and there's no improvement after a particular level. So whenever it goes constant for a few epochs, then it'll probably take that. Same thing, scaling, splitting, and then so this is where we're defining the early stopping callback. And then patience is 10, that is what we're setting the patience as. So first thing, with compiling a model without early stopping, so there's this two layers compilation using Atom Optimizer, all of that. And then here we are doing it with early stopping. So as you can see, we have a callback set here with early stopping parameters. Whatever we defined here will be called here. We're just evaluating both the models. So as you can see, without any early stopping, we got 0.97, and then with early stopping, we got 0.98. So this shows that the model trained with early stopping achieved a higher test accuracy compared to the model which was trained for a fixed number of epochs. So yeah, this is all about early stopping. Let's go to the next one, which is nothing but the Monte Carlo dropout. So in this, what we're doing is, yeah. So in this, what we're doing is we're demonstrating how to use dropout at inference time to get a distribution of predictions which can be useful for uncertainty estimation. So let's see. So we're going to run the code and then observe the mean and the standard deviation of the predictions. Higher standard deviation indicates higher uncertainty, is what we have to show. Uh, so unlike standard evaluation where dropout layers are turned off, Monte Carlo dropout involves keeping the dropout layers active during inference, so that by keeping them active and performing multiple forward passes with dropout enabled, we can obtain not only a prediction but also estimate of how much the model is uncertain. So greater the standard deviation, greater the uncertainty of the model. So we're doing the same thing, model with dropout, compilation of that, and then this is where we're doing the multiple predictions using the dropout enabled. So this is where we're doing the Monte Carlo dropout. So you can see that the accuracy is 0.983, which is better than before. So we can see that uh, it did improve the prediction robustness, and also the uncertainty estimation is also done. So higher variance or entropy suggests that there's lower confidence in prediction. So we didn't calculate uncertainty in this collab, but the process generated multiple predictions layers the groundwork for doing so. So the high accuracy achieved with this dropout suggests that this task and this model keeping dropout active during an inference can lead to like good generalization performance. So this is all about using Monte Carlo dropout. So let's go to the various initializations. So in this we're showing how to use different weight initialization strategies in Keras layers and when to use them. So we have three different ones: GLO, ROT, normal, HE normal, and Leaken normal. So basically how we are going to initialize weights. Okay, so this is about the various initializations. And then we're gonna compare them too. So we have zeros, random normal, GLO rot normal, and HE normal. So Javier normal is nothing but this one, and then HE normal is also known as the MSRA normal. So we're taking the same data set, scaling the data set, splitting it, and then creating the model with this Javier normal. So this is the creation, and then we're defining the initializers to test basically, and then training and the evaluation of models with different initializers. And then we're just plotting the history to check. So with zeros it was 0.07, and then with random normal we got 0.972. With heavier we got 0.97, and then with the HE normal or the MSRA normal we got the 0.97. So these are two similar ones as you can see, and here also there's a difference of like 0.05. So these are the different ones. They are on par, but you can still see the difference. And then these are the results that I have, how much accuracy we're getting. So the one with the zeros initialization was a one that performed bad because we got 0.707 as the accuracy. And then with the normal it was still better, but I would say with heavier or uh, the MSRA normalization, that is what did better. And then we also did the alpha beta testing by comparing it with the zeros. So this is all about various initializations. Let's go to the next part where we're doing batch normalization. So here we're doing various batch normalizers to stabilize training and potentially improve the generalization. Let me open the next. So this is the batch normalization where we're using batch normalization in simple neural network. So this is a technique that normalizes the input of each layer for each mini batching during training. So this can lead to like faster and more stable training. That is why we use it, and it also allows higher learning rates and also improves the generalization of the model. So we're gonna do two similar neural networks. So one is without the batch normalization, and then one is with the batch normalization. As you can see, this has just two dense layers. Then we just compiling the model and then fitting it. You We already have defined the train test everything, so fitting it. And then we have the batch normalization over here. We have one activation layer with the ReLU activizer. We have batch normalization and then two dense layers as before. So the same thing, loading, fitting, everything is done here. Plotting graphs. So as you can see, without the batch normalization, we got 0.972, and then with batch normalization, we got an accuracy of 0.97. So there was a difference of 0.05. So you can see the accuracy comparison over here. It was still better than without using the batch normalization. So it is better to use batch normalization, So you can see that the validation loss for the model with batch normalization appears to decrease more smoothly and plateaus at a slightly lower value compared. So you can see plateaus at a more simple, slightly lower value compared to the model without. And the one without patch normalization, it shows a lot of fluctuations, as you can see. And also the accuracy also it grew rapidly and reached a higher plateau compared to the one without. So yeah, this is the importance of batch normalization, I would say. And then the next part is using custom dropout and custom regularization. So we can create our own custom dropout layers based on activation, and also custom regularization techniques by implementing cu custom layers. So let's go to that. So we have two here. This is for the custom dropout. This is for the custom regularization. Taking the same data set. This is how we define the custom dropout layer. So I've defined everything that I require for that training, for what is for training, and this is the in function. So this is for the custom regularizer, and then I am using something similar to the L1 regularizer, and then creating a model using the custom dropout and regularizer, and then just defining, and then I have the custom dropout here, and I gave it as 50%. Creating a model based on that using training, testing, everything, and then comparing with a model using a standard dropout and L1 regularization. So basically, these are my custom values that I've given defined over here with these two. So you can see custom dropout and then custom L1 regularizer. And then this second model that I have is nothing but using the normal L1 regularizer. This is nothing but 1%. And then I have a standard dropout layer. So I'm just going to compile this model and that model and compare both of them. So you can see that with my custom regularizer and the dropout, I got an accuracy of 0.93. And then with the standard dropout and L1, I got an accuracy of 0.98. So here I would say that the standard one performed better, but there might be cases where the standard ones don't work fine and we have to create our own custom layers and custom regularization methods. So yeah, this is all about custom regularization. And then we also have okay, I'm gonna split this into two parts maybe because this video has come till 17 minutes. So we're done till custom dropout and custom regularization. So in the next part, I'm going to continue with IH, which is nothing but using callbacks and TensorBoard. Thank you.